Welcome back to elementary statistics. In this video, I'm going to wrap up our discussion of abstract probability with the ideas of conditional probability. We've seen conditional probability already. When you have two events which are not independent, the probability of A and B is equal to the probability of A times the probability of B given A. Right? That's our product rule for two events which are not independent. And if I simply rearrange this equation just a little bit, I arrive at this version, which is known as the conditional probability formula. I think I mentioned it before, but this construction over here, P of B given A, is called the conditional probability of B. It is the probability of B under the condition that A has occurred. And we talked about the addition rule and the multiplication rule, and we were able to build up some ideas on that that work really effectively when you know a bunch of probabilities. But when it comes to experimental probability, very often the arrangement of this is a little bit awkward. And so being able to use this formula effectively really comes into its own. Let me get my head out of the way and let's jump into an example. A bird watcher is excitedly identifying the finches passing through her neighborhood this week. For each finch, she identifies it as male or female based on the pattern on its wing, and then also records if the beak is rounded or pointed, which indicates which species of finch it happens to be. And she's taking this information and arranging it onto a 2x2 frequency table. All right, so we're going to construct this table with 2 rows and 2 columns. I guess 3 rows and 3 columns, including the header. The rows are labeled as male and female. The columns are labeled as rounded and pointed to give the place to record the wing structure. And this bird watcher is counting down tally marks. I'm not going to take the time to write down all the tally marks, but after she's completed her bird watching and the finches have migrated past the neighborhood, she totals everything up and writes it down using numerals and finds that she spotted 13 males with rounded beaks, 17 females with rounded beaks, 21 males with pointed beaks, and 16 females with pointed beaks. All right. And with that summary, we have to do some thinking to figure out what we are looking at and how we can proceed with this data. First of all, kind of the easy one, if we add together the numbers in each of these categories, 13 plus 17 is 30, plus 21 is 51, and then 16 takes us to 67 finches that this bird watcher has spotted. Right. The probability that the bird watcher has spotted a male finch is asking, what is the probability that I fall somewhere in this row? A beak can either be rounded or pointed. That's a clear distinction. No finch has a pointed and a rounded beak. That would require a finch with 2 beaks to be in 2 separate species. So the number of male finch is 13 plus 21, or 34, and then the probability is 34 divided by 67. I'll report that as a decimal in this case. It comes out at 0.5 0.507. We could also ask questions like, what is the probability that a finch that came through had a pointed beak? Well, looking at this column, there are 21 and 16. All told, that's 37 of the 67 finches spot, which is about 0.552 as a decimal number. Right, and I always use decimals when it comes to experimental probability. Fractions have a connotation of exactness that we don't have in these cases. Right. Continuing onward, I'm running low on room here, so I'm going to take this table and just copy it a little bit lower so I can keep it on the screen while we keep working. And I wrote that pretty big, so let's shrink it a little bit and continue onward. We were able to calculate the probability of having spotted a male finch. We were able to calculate the probability of having spotted a finch with a pointed beak. Now we get to start into some of the interesting questions. What is the probability that the finch was male, given that it had a pointed beak? Well, because we know that this finch in question had a pointed beak, we can throw that part of the data points away. We only have to deal with these data points. And in these data points, there are only 37 finches in the entire story. 21 of them were male, and 21 divided by 37, according to my calculator, is 0.568. Continuing. The probability of the finch having a pointed beak, given that the finch was male. In this case, I know that I'm dealing with a male finch. The female finches are no longer in the story, they're no longer in the picture. And so the total number of finches that I'm studying is just 13 plus 21, which is 34. And the ones with the pointed beaks, there were 21 of them. And my calculator is happy to tell me that 21 divided by 34 is approximately 0.618. And the real reason that I wanted to go through this example is to just emphasize that conditional probability changes depending on which direction you go. The probability of male given pointed and the probability of pointed given male are not the same probability, and they almost never are. All right, I'm going to look at the same situation again, but this time, instead of looking at one bird watcher's report, I'm going to look at some aggregated data. So we're still looking at male or female. We're still looking at, let's not cut off the words I'm writing. Rounded or pointed. But this time, because we're looking at aggregate data, instead of giving these values as whole numbers, the number of birds spotted, the data is actually going to be presented as probabilities. And I'll present the probabilities as percentages. All right, so I have 21%, 27%, 28%, and 24% as my probabilities. And even though these are now probabilities and not counts, it doesn't change anything at all about how to perform the calculation. If I want to calculate the probability that the finch I spot has a rounded beak, given that it was female, well, the formula told us that's the probability of round and female, 27%, divided by the probability of female in general. Well, that's either the round, 27, or the pointed, 24. And I can actually ignore all the percent signs, just multiply top and bottom of the fraction by 100%. I get 27 over 51. Then when I perform the division, I get percentages again. Excuse me. 0.529, or about 53%. All right. So that's the idea I wanted to talk about here. We can take our idea of a frequency table and we can extend it out into 2 dimensions. I could extend this a little bit further even. I could have more than just 2 categories in this direction. I could have more than 2 categories in that direction. If I have more directions, right? So I did male and female, round and pointed. If I was also looking at finches and jays, writing it on a table would start to get to be very difficult, but the theory would still work and all of the ideas would still be the same. Right. For discussion on this topic, once again, just very generically, we're thinking about probability in a very generic sense. And the idea here of experimental probability, thinking about experiment, thinking about the difference between experiment and theory. Have you run into places where figuring out a probability by experiment like this has been something that you've needed to do or needed to use in another course? If so, what was it? What interesting things did you come across there? Were there any questions that you wished you could have answered, but you weren't comfortable with probability yet? And best case, are there any of those questions that you're able to answer now that you couldn't before? Right. That's all I have on this one, so I'll wrap up here. Thanks as always for joining me. I'll see you next time.